AI is everywhere. Dolphin Gemma aids cytologists in their quest to decode dolphin communication. Anthropic's Claude suggests routes for NASA's Perseverance rover as it explores the surface of Mars. OpenClaw, your personal AI assistant, can book your vacation, but you might not want to give it your credit card just yet. If you've ever wondered how AI works, you're in the right place. Welcome to the Data in the Story, where we deploy curiosity as our defense and offense in a fast-changing world. I'm CJ Washington. This is the fifth in a series of primers that explore how AI learns. Many Data in the Story episodes, from extending the human lifespan to the future of work, will touch on AI. And to better focus on the big picture, I'll send viewers here for the details about how AI works. We've covered artificial neural network, supervised learning, unsupervised learning, and reinforcement learning. If you're thinking, this journey has been fun and I've learned a lot, but I just had an in-depth conversation with Gemini about my career aspirations, and I want to know how it works, this is the primer for you. We're going to talk about language models, transformers, self-supervised learning, and reinforcement learning from human feedback. We'll discuss scaling and the capabilities that arise as these models get bigger and they're trained on larger data sets. If you're new to AI and you haven't seen the primers on artificial neural networks, supervised learning, and reinforcement learning, I suggest you watch them now. The primer on unsupervised learning is also good, but it isn't a prerequisite for understanding large language models. What makes a language model large? It comes down to parameters, the internal weights and biases the neural network adjusts as it learns. While a standard model might have a few million, a large language model scales it up to hundreds of billions of parameters trained on trillions of words. Machine learning exists on a spectrum. On one end is unsupervised learning, where a model groups unlabeled data by discovering hidden patterns. On the other is supervised learning, where the model learns from data labeled by humans. LLMs use a middle ground called self-supervised learning. Instead of relying on human teachers, an LLM trains itself using a simple game. Predict the next word. By looking at a string of text and guessing what token should logically come next, the model uses its training data as an automated grading key. In the LLM's 10 trillion words of training data, from books, web pages, basically the entire internet, and any other data that engineers can get their hands on, it might encounter the phrase, "the dog ate his." Instead of reading the next word, the model is challenged to predict it. To do this, it assigns every word in its vocabulary with a probability of being the next word. Its loss function then checks the next word against its probabilities to see how it did. If the next word is shoe, and the model assigns shoe a low probability, the loss will be large. Using backpropagation and optimization, the model's parameters are adjusted such that the next time it sees that sequence, shoe gets a much higher probability score, and incorrect guesses get lower scores. Hopefully, the process I'm describing is familiar from the primer on supervised learning. It's similar for LLMs with a twist, and that twist is the transformer. Invented at Google in 2017, the transformer is the architecture that makes the LLMs we're familiar with possible. Transformers implement self-attention, which allows LLMs to efficiently model how the tokens in a sequence relate to one another. A token is just a chunk of text. It could be a word like run, or a suffix like ing. Let's step back and take a look at our training data. What is a sequence? In the context of LLM training, a sequence is a training example. It could be a news article, it could be a full book. Each sequence is tokenized, and during training, an entire sequence is fed into the transformer all at once. The model analyzes these tokens using a mechanism called self-attention. For any given token, self-attention calculates a relevance score between it and every preceding token in the sequence. Consider the sentence, "The cat ate the mouse because she was hungry." When the model processes the word she, it looks back across the entire history of the sentence. Even though she is physically closer to mouse, the attention mechanism assigns a much higher score to cat, dynamically tracking the true context across long distances. LLMs use decoder-only transformers, meaning the tokens only pay attention to tokens that precede them. Therefore, she will not calculate attention scores for was or hungry. Our goal is next token prediction, so we want to use previous tokens to predict future tokens, never vice versa. Transformers were a paradigm shift from recurrent neural networks, RNNs, which process text one token at a time. As a brief aside, the graphical processing unit, GPU, the favorite chip of machine learning practitioners, is designed for parallel processing. During training, RNNs are restricted to processing a single token at a time along the sequence, leaving a lot of compute on the table. Transformers, on the other hand, process entire sequences simultaneously during training, perfectly exploiting the parallelization of GPUs. More problematic, during training, a phenomenon called vanishing gradients makes it difficult for RNNs to learn long-term dependencies, effectively causing them to ignore tokens from the beginning of a long sequence by the time they reach the end. Back to our sentence. The cat ate the mouse because she was hungry. You and I know that she attends strongly to the cat because we understand the relationship between cats and mice, and we have experience with hunger. How do LLMs know? Let's get into the nuts and bolts of attention. At each layer, the transformer projects the embedding for each token in the sentence into three distinct vectors. The query vector, what I, the token, am looking for. The key vector, what I, the token, offer. And the value vector, the information I, the token, carry. How does it create these vectors? Transformer layers contain weight matrices. A matrix is simply a grid of numbers, in this case, a grid of weights. Each layer has a query matrix, a key matrix, and a value matrix. The query vector for she is calculated by multiplying the embedding for she by the transformer's query matrix. The key and value vectors for each token are calculated in a similar manner. The embedding of the token is multiplied by the key matrix to get the token's key vector, and the value matrix to get the token's value vector. In our example, we now have the query vector for she, and we have the key and value vectors for each word preceding she. We calculate the attention score for cat by taking the dot product of she's query vector and cat's key vector. She's query vector represents what she is looking for. Cat's key vector represents what cat is offering. The dot product measures the similarity between two vectors. So the dot product for she and cat should be higher than the dot product for she and mouse. The transformer calculates the attention score for each token preceding she, and then uses the softmax function to convert these raw attention scores into percentages that sum to 1. Those percentages determine how much each token's value vector will contribute to the final transformed context-aware embedding of she. Now that we have the details, let's connect the dots back to our original question. How does the LLM know that she should attend more strongly to cat than to mouse? Remember, the goal of an LLM is next word prediction. They use attention to predict the next word. During training, when their prediction probabilities are off, the loss function captures this, and backpropagation and optimization are used to update the weights in the query, key, and value matrices, such that the LLM makes better predictions. In so doing, these matrices become tuned to provide better attention. The top-line goal is next word prediction. The context it needs comes from attention. Each layer of the transformer builds on the one before it, capturing increasingly abstract features of the relations. By the time the data reaches the final layer, the model has transformed the input into a dense map of context, giving it everything it needs to calculate the probability of the next token. What I love most about AI is observing the mechanisms of learning. If your top-line goal is to understand the math underlying AI, how does your brain accomplish this at the neural level? I wish I knew. The architecture for a model like Gemini might have 100 or more transformer layers, with each individual layer containing its own dedicated feed-forward network. Training a model of this size requires massive amounts of compute and time. 3 to 6 months of continuous 24 hours per day training on a cluster of specialized chips, like NVIDIA's GPUs or Google's TPUs. I've been using the terms token and word interchangeably, and this misses a bit of nuance. A token is a fundamental unit of a language. To humans, words as tokens make sense. Sentences are composed of words, and we tend to focus on the meaning of words. Words don't have meaning to LLMs in the way they do for us. In fact, words are problematic for LLMs. For one, there are too many unique words, and the vocabulary would be too large. It would make the LLM vulnerable to typos and misspellings because they don't appear in the vocabulary. LLMs learn best when tokens are based on frequency in the training data and reusability. Consider the tokens ing and ed. They provide similar information for many English verbs and are highly reusable. For those reasons, subword tokenization is a popular choice for LLM text. Common English words typically end up as a token, while rare or long words are broken into recognizable chunks. Now, we have a pre-trained LLM that is a master next token predictor. Why is it called a large language model? We've already established that it's large. In simple terms, a language model produces a probability distribution over sequences in a language. Let's break that down. A probability distribution is a guess at how likely a sentence is to appear in the real world. Winning gymnasts are athletic. Great sentence. Winning gymnasts are backpack. Statistically improbable. An LLM at its core produces language that is statistically likely to be correct. The human brain does something similar. As you process the meaning of language, your brain produces what neuroscientists call N400 waves. The N is for negative polarity, and the 400 means it occurs roughly 400 milliseconds after the stimulus. When I say, winning gymnasts are athletic, the N400 wave produced by your brain is small because the sentence is predictable. When I say, winning gymnasts are backpack, the N400 wave is large because your brain's prediction has failed and now has to work harder to process the unexpected text. P600 waves are produced as your brain processes grammar. A child saying, she teached me, stimulates a large P600 wave. Learning to predict the next token in a sentence is not a trivial feat. In order to do this successfully, the model must build sophisticated internal representations of language. As we increase the number of weights in these models and flood them with data, this ever-increasing internal complexity unlocks emerging capabilities. As AI researchers at Google have noted, if you train a model on 1 million tokens, it predicts mostly random gibberish. If you train it on 1 billion tokens, it maps basic syntax, subjects, verbs, objects. By the time you scale up to 10 trillion tokens, the model's internal representation encapsulates the underlying logic and patterns of human thought. This complexity is a requirement for accurate next token prediction. As impressive as it is, we still don't have the version of ChatGPT you've come to know. The second phase of training teaches the LLM how to be conversational. Our pre-trained model has learned about the world, but it doesn't know how to formulate responses. If you ask, for example, when was Alan Turing born? It might respond, where was Alan Turing born? When did Alan Turing develop the Turing machine? Its response is related to your prompt, but at this stage, the model is prone to rambling and doesn't know how to follow instructions. Supervised learning is used to train the LLM to be conversational. The model is given prompt-response pairs. We can think of these as labeled prompts. The model reads the prompt and attempts to predict the best response. The model's loss function compares its predicted response to the provided response and adjusts its weights through backpropagation and optimization until it reliably predicts high-quality responses. Once the LLM has learned how to be conversational, it must be taught how to behave. This third phase of training is accomplished using reinforcement learning from human feedback, RLHF. In this phase, the model is given a prompt and generates a few different options for a response. Human reviewers rank those options based on the Triple H framework: helpfulness, honesty, and harmlessness. Imagine the prompt asks for a workout plan to finish your first 5K. If response A says, running is miserable, the human ranks it poorly for not being helpful. If response B suggests running 10 miles a day and links to a performance-enhancing drug website, the human flags it as harmful. But if response C provides a reasonable, steady training plan, the human ranks it at the top. These human preferences are used to train a system that acts like an automated judge, grading the LLM on millions of conversations until it automatically favors helpful, safe paths and completely avoids toxic ones. Models are safe and well behaved because of RLHF. Using human feedback, however, does create some thorny side effects. Research has shown that when it comes to complex tasks, human raters often prefer inaccurate answers that sound confident over correct, nuanced answers. This can lead to models learning to prioritize confidence over nuance. Another issue resulting from RLHF is the trap of sycophancy, when the AI prefers flattery and validation over truth and safety. Human raters, being human, like to be validated, and they give higher ranking to answers that validate them. So if you say to a sycophantic model, "I'm a couch potato, and I intend to fix it with a rim-to-rim hike through the Grand Canyon next week," it might reply, "That is a bold and ambitious plan to take charge of your health. Would you like me to check affordable airfares for you?" A friend hopefully would advise you to spend a few months training. In addition to RLHF, models like Anthropic's Claude go through an extra phase where it trains on a constitution, a written set of principles the model should abide by. During this phase, the model critiques its own responses and revises them to align with the principles of the Constitution. Over millions of iterations, it internalizes these values. If you're interested in reading Claude's Constitution, it's available on Anthropic's website. Once an LLM is trained, it's finished learning. Continual learning, the ability to update a model without the risk of catastrophic forgetting, is an active area of research. Until it's figured out, we have retrieval augmented generation, RAG. Say you're watching the news and there's a breaking story, so you pull up Gemini to discuss it. You're referring to a current event, so it isn't in Gemini's training data. How does Gemini provide a reasoned response? A separate retrieval system performs a live web search, grabs the most relevant text, and inserts it into your prompt. Gemini then reads the prompt, including the retrieved context, and formulates a response. If you're interested in LLMs and how they came to market, I recommend Supremacy by Parmi Olson. Olson, a tech journalist, has written a fast-paced narrative focused on the personalities involved in the AI race. She structures her narrative as a battle between Sam Altman of OpenAI and Demis Hassabis of DeepMind, but she avoids the myth of the lone genius by covering many other contributors to the field. I mentioned that the Transformer was invented at Google in 2017. It was a collaborative effort by a team of researchers. Fortunately for the world, or unfortunately if you happen not to like LLMs, their discovery was published in a famous paper called "Attention is All You Need." While Google used the Transformer to better understand language to improve search, researchers at OpenAI applied it to next token prediction at a massive scale. You know what came next. If you want to dive into the math of AI, and you want an entertaining book to guide you, I recommend Why Machines Learn by Anil and Nathaswamy. I discussed the book in detail in the primer on neural networks and shared some important caveats before reading it. The original publication didn't cover transformers, so you'll want the paperback edition, which includes an afterword on them. Keep your curiosity strong, and whatever you're curious about, I hope it leads you back here, and I hope you find what you're looking for. Curious about how GPUs work? Or maybe you're wondering, what is a GPU? Subscribe, turn on notifications, it's coming. To the data in the story.